Today at our last seminar of the year, our Ulysses Neuro Seminar. The next one will be in January, but Disha will give you more information at the end of it. Today we welcome Dr. Brian Murphy, and he has a very impressive curriculum that I'm not going to read entirely, but just so you know, his career started in internet startups around the world, and he has trained in computer science in Trinity College, in cognitive neuroscience at University of Trento, and machine learning at Carnegie Mellon University, where he had the chance to work with Professor Tom Mitchell on brain reading techniques for detecting cognitive states from recordings of neural activity. And in the past 15 years, he has mostly worked on machine learning and other analytical methods to better understand the human brain and mind. He is founder and CSO, Chief Scientific Officer at Cumulus NeuroScience, was developing the leading platform for large-scale and broad-spectrum of objective assessment of brain health based on gamified assessment and consumer-usable EEG recordings. And I leave the floor to Brian for this. So thanks for joining us today.
Yeah, thanks, Fabiana.
Thank you.
Hiya, nice to meet you all. So I know there are all of you there, and hopefully people online through that camera over there can see me too. As Fabiana said, my name is Brian. I did originally my PhD here, and we now have a company. It's Cumulus NeuroScience. It's mostly in Belfast, but we also have a small office here just across the river in the CHQ, Dogpatch Labs. There's 5 of us working there, basically the analytics team, machine learning team, and some of the scientists. We have a lot of relationships with the university, so we've done a few joint studies together with Rob Whedon's lab particularly. And also we have, I don't know if any of you know Florentine Barbet. She's a PhD student of Rob's, who's also an employee of ours. She did one of those industry PhDs, which are great with industry postdocs as well with SFI and IRC. And we also at the moment have a study running with Orla Hardiman, who was a TCD academic and a clinical consultant in Beaumont. And this is kind of a mixed thing. So I don't know, I guess, is everyone here somehow kind of an academic or student or postdoc or something of neuroscience or cognition or something like that? Because it was meant to be, I was told it could also be a general public. I suppose there could be people watching on the side. So basically the first half is kind of like, here's the big story and the big dream and everything. And then the second half gets much more methodological. And hopefully that thing, we write the verb kind of the world's leading XYZ. You can make your own decision whether we are or not based on the evidence I'll show you. But hopefully this will, if I click this, that should.
Oh, sorry. Try again then.
Try again then. Okay, cool. All right. Okay, so why do we bother? I'll start talking about dementia. So depends on which publication you look at. 1 in 4, 1 in 3, 1 in 2 people will end their life with dementia. So it's a really huge problem. There are some, there's I think some things are better is that as we get generally healthier and live healthier lives, the proportion of people who have dementia at a certain age goes down. But because there's so many more of us in other age brackets, the total number is going up dramatically. And it's not just, we have enough trouble in countries like Ireland and the United States and Germany dealing with this. Obviously, think of all the people in India and China and Nigeria and Turkey and Brazil and all the countries that, there are loads of countries with hundreds of millions of people who just don't have good solutions for this. Again, even in countries with the best resources, it takes a long time to diagnose Alzheimer's disease dementia. And it's very hard, it's surprisingly hard to diagnose it as well. It can be confused with other things, like you may have somebody who say, gets dementia at an unusually early age, and they come in, people say it's probably stress, it's probably depression, it's probably something else, right? Or you get somebody who comes in late with these sorts of symptoms, people say it's probably dementia when in fact it's depression, right? So these things like that can be confused. It's surprising how hard it is. And that same difficulty with understanding disease also hits the success rate for CNS drugs. So Alzheimer's is a particularly good example of a disease where we don't have good solutions. We have a certain set of drugs which will basically kind of slow the decline of symptoms for some time, but the effect tends to wear off, or people stop tolerating it because of side effects, and people stop taking the drugs, and they're kind of, imagine you're kind of in decline, the drug kind of holds it off for a while, but then when you stop taking the drug, you basically end up where you would have been if you hadn't taken it at all, right? So it's like a temporary reprieve a temporary partial reprieve. It's just not good enough. So this is Alzheimer's, and the biggest problem is detecting, characterizing, phenotyping. Okay, phenotyping is for people who aren't familiar with the term, is having a detailed understanding of how a particular disease is affecting an individual person, right? And also what are their, I suppose, biological, or what are their characteristics that will affect both the way that disease, that biological disease affects them, and also the way that any therapy may work for them. So it could be your genetics or your age or your gender or your socioeconomic background, or whether you grew up in an environment with a lot of, particulate, pollution, etc., etc., etc. There are all these things that may have an effect, and often in ways that we don't 100% understand either. So that's Alzheimer's. You can think as well about psychiatry, where you have loads of, certainly there are a lot of great people developing new therapies for psychiatric conditions, but for a lot of psychiatric conditions, especially depression, there are loads of therapies which are very effective for many people. They're also not effective for some people, and some people do very well with no pharmacological intervention at all. But for those people where they could get an effective existing drug, often there's a very, very long process in trying to decide what is the right drug for them. Or let's say, okay, trying to guess or estimate, make an informed decision of what is likely to work for them, and then actually detecting whether it's working, right? Those are hard things to do. And if you look at why these things are hard things to do, the way we do things is not especially surprising. So again, in psychiatry, most of diagnosis is around clinical interview and questionnaires. And you have the situation where somebody's, I'll say in my family, we've had, relations and also broader circle of friends, some people with very serious psychiatric conditions, and this can lead to death through suicide. And it's not just a lifestyle problem, as I think, I think that's changed. There used to be maybe stigma and a lack of understanding. I think people understand now that's a serious thing. But it can be hard to characterize and then tell whether things are working, where you've got somebody in this distressing situation where you give them a drug and then you say, now, are you better? After a week, and say, after 2 weeks, are you feeling better? After 3 weeks, you're feeling better. After 8 weeks, you're feeling better. You're like, well, maybe I'm feeling better, maybe I'm not feeling better. I don't know. I'm depressed. Or maybe today's a good day. You know what I mean? Or maybe people put a brave face on it. Feel kind of obliged to or feel social pressure, obliged to put a kind of a better spin on it, or whatever. Anyway, it's not the most reliable way of detecting therapeutic efficacy, right? If you look at Alzheimer's and other neurodegenerative conditions where there's often a clearer kind of biological basis that we have some understanding of, then you can look at, very usefully, you can have proteins. You can use PET scanners or lumbar punctures to pull out spinal fluid and look for particular proteins which are associated with Alzheimer's disease. You've probably heard of amyloid plaques and tau tangles. Now, challenges with them is right now you have to go into a big radiological, a big scanner, of which I'm not sure. I don't know if we have amyloid PET scanning in Ireland, do we? Not sure. Okay, it's not widespread. It's not something that kind of everyone get diagnosed with easily. So then you've got an option of lumbar puncture. If you did have a PET scanner, it costs thousands of pounds or dollars or euros, and it's a massive radiological dose. Or you get a lumbar puncture. People aren't lining up around the block to get a big needle stuck in their spine. And then even if you have them, now they're about to be replaced, we hope, by blood biomarkers. We just take a blood draw, look at the plasma, and get a rough idea, not as good an idea, but a rough idea of those things. But even if you do, the problem there is it tells you something about your underlying biology, but the association is quite loose. So there's some people with elevated, too much amyloid or more amyloid than you expect, but they're actually okay. And then other people don't have high amyloid levels, but they've clearly got dementia. So it's a loose association, it's not 100% understood. And anyway, even if the person's got dementia and they've got high amyloid, for example, that level of amyloid doesn't tell you anything about the progression of their symptoms, of how they're feeling, how they're operating, whether they're still able to drive their car, manage their financial affairs, remember where the keys are, and so on and so forth. So you've got biomarkers don't work great. Then you've got clinical interview, where again, think of Alzheimer's, tell me whether over the last 6 months your memory's got better, or you've got a memory disorder. So it's clear that's got limited utility. Or you're doing different sorts of paper and pen tests, which again, everyone knows are useful, like the MMSE or the MOCA, these screening tests, which are useful as a start, but very kind of coarse-grained. So there are a lot of reasons why we would like to improve the way we measure the condition of individual patients in neuropsychiatry and neurodegeneration. And kind of here's a picture of what we'd like to have. So what you'd like to have is you'd love to look at, and this is like dementia, neurodegeneration. I don't know if you can see the subjective impairment here, that there's an early stage where people come in and they say, okay, I'm feeling a bit funny. I don't feel like my memory is as good as it used to be, but I'm not sure. And a certain proportion of those, that will be an impression that's impossible to confirm, and it may or may have never been a problem. Other people, it's real, but it's caused by something else, like say a sleep disorder or stress or something else, or they could be in the early stages of dementia, right? Then you go into mild cognitive impairment, where there is a detectable, like a clinician can detect that somebody's, say, memory is less effective than you would expect for somebody of, say, their age, education, socioeconomic standard, gender, or whatever. And but you don't yet quite know which disease may be causing it, right? And then over time, the disease will get more severe, and then it'll be easier to differentiate. And you might then, after a while, be able to tell the difference between Alzheimer's, Lewy bodies, or Parkinson's dementia, frontotemporal dementia, or vascular dementia, for example. And I mean, we do know from large-scale research that there are a lot of different aspects of these diseases, aspects of patient condition, which are associated with these diseases. So you'd like to be able to measure memory, executive function, which is kind of how effectively you can pay attention to things and make decisions, language, mood, motivation. I'll leave cognitive reserve for now. We can talk about it later if you want. Sleep and motor function. These are all things that may be affected in different ways by these different diseases at different times. And we know at a population level that if you go early in Alzheimer's disease, most of your cognitive functions will be relatively okay, but your memory will be impaired. Unusually compared to other things and for your age and education. If you go later, all of those things will eventually be impaired. If you went early on in frontotemporal dementia, you might see particular effects on language and executive function, and then later on, everything gets impaired, and so on and so forth. So we know that to be true at a sort of population group study level. We know also that different diseases have different characteristic patterns over time, and when they how they develop, how they progress, and kind of the pattern in longitudinally. But we can't see that for individual people. It's just not achievable, or well. And I think, and the thing is, well, it hasn't been achievable, but it's now becoming achievable, and that's what we're trying to put together. So I'll show you. So we do need better diagnostics in general in healthcare, and we do need better data for trials. So exactly all those problems of not being able to understand a patient's condition stops people who develop a new therapy from getting the right people into their trial, because usually it's for a particular drug. Like, you don't want to run a trial about early Alzheimer's disease and then discover several years later it didn't work, but discover that, say, 20% of people that actually had frontotemporal disease. There's no reason to expect that this Alzheimer's targeting drug would work for them. And then you also want to be able to detect change in that trial better, right? So you want to have finer instruments for detecting change to see if the drug is working. The reason you want to do that is because you don't want to have to run a study where you've got 5,000 people for 5 years when you could do with 1,000 people in 2 years, right? Because number one, it would be longer before a working therapy would get to patients. And number two, because that 5-year, 5,000 person study costs, I suppose, a lot more than a 1,002 person study, 2-year study. And with that same amount of money, the pharma company could try 10 drugs or 5 drugs rather than 1 drug, right? Then you increase your chances of success. So this is what we do, and these are the companies we work with. So we've been around for some of our core technology we've been developing for about 7 years now. But about 2 years ago, we got in contact with the Dementia Discovery Fund. So they're a venture capital fund. They're venture capitalists. They're part of SB Health Investors, which is a big American venture capital fund. But they're a sub fund within that who purely, exclusively invest in therapies for dementia. That's all they do, right? And they sat down with some of their investors. So these 5 companies at the top are kind of sub-investors into Dementia Discovery Funds. They added to the pot of money to invest in new therapies. And they sat down and said, okay, we've got all these great new molecules and everything. We think they, for all these different reasons, they have a good chance of working on different mechanisms, but we don't feel like we've got the right tools to recruit the patients and test whether they work or not. And then since then, we've had another 5 companies join us. So we're very lucky in the company to have representatives of all those 10 companies. We meet them on a monthly basis, and they basically tell us, if you want to detect change in dementia, these are the things you should measure, and this is how. And these are the sorts of trials you should run or studies you should run to confirm that it actually works, right? So I will go on. Yeah, and these are the areas. When we talked to them, they said you want to measure cognition of various types. So I already said, you might want to measure memory for Alzheimer's or executive function for Lewy body's dementia, or language for frontotemporal dementia, or each of those things. They also wanted to measure EEG, so they don't want to only be measuring the indirect effect of changes in brain function on your external behavior, but also measure your brain function itself directly, okay? And they wanted to measure mood in various ways and language. This was kind of they actually also asked us to do something with sleep, which we're at a less advanced stage with, which is something we're going to add. But their point was you want to be able to measure all of these things, and you want to be able to measure them frequently and easily and objectively. And that means you should at least also be able to do them in the home. So you have to build a kind of technology which anyone can take and bring home and use, say, 5 days a week for 3 months or something like that, which sounds like a lot. And again, I'll show you some data about how kind of feasible that is. So this was our brief, and these are then the tasks, the tablet-based tasks, the computerized tasks we've developed to tap these different areas. We can go again into them in detail. People are, I don't know if there are people here who are kind of into the neuropsychology of these diseases and know the difference in recognition, memory, and recall, and blah, blah, blah. We can go into that later if you'd like. So let's go back to where we're coming from. So one important thing here is there are a lot of people. So I've got a machine learning background, I've got a software background, I've got a neuroscience background, and you could come up with something 100% new. Now, if you do, that'd be great. So a totally novel task, and kind of put a layer of fancy AI on top of it. The problem with that is that pharma scientists who understand the mechanisms of disease and understand the mechanisms of drugs may say, well, what does that really mean, right? And clinicians would ask the same question. They'll say, okay, have you just given me another tool that purports to tell me something, but I don't know whether to believe it? Because I think doctors don't have lack of information. They may have too much information. It may not all be telling them. A lot of it may be conflicting, and they're kind of uncertain how much they can trust it, right? So what the approach we've always taken is to say, if we want to measure something, like say we want to measure an objective measure of decision making and executive function, let's go into the literature and see what have people been doing for the last 40 years and take that. So this is any of you who are familiar with EEG research may have heard of the P300. It's kind of like the most studied time-bound EEG metric. And in a typical P300 experiment, somebody sits down in a lab like this, has wet EEG put on them. Setup, depending on the number of sensors, may take something like, say, 45 minutes or something, maybe longer, maybe shorter, whatever, it depends. And that's the other thing. Some labs are kind of really quick, and some labs are slow, and which is important because it can change the characteristics of the signal. Right, because some labs think, okay, time is important. I don't want to overburden the patient. I'll just go easy on them. And other labs are, I am going to get the best data. I've got this person. I'm going to get the best data I can, and they take longer. And in any case, it takes a while. And then afterwards, people need to wash their hair, which doesn't sound like a big deal, but if it's ever going to be in a clinic, it's a big deal, right? So you need to have like well, okay, first of all, a lot of people don't like their hair getting messed with, right? That's one thing. I'm not either anyway. But it takes time, right? And then you would get in, and then you would see some task where, say, there's a screen that says, if you see some green shape or other, you don't have to respond. And if you see a red circle, you do press a button, and do that for 20 minutes. And that's not unusual. And then at the end of the 20 minutes, you look at you've got this EEG, 20 minutes of EEG, you've got little events in it to say this is when the person saw something they should or shouldn't respond to. Here's the reaction times, and you pull out data that gives you this waveform. I'll show you some examples of in a little while. Now that works once in a lab if you've got somebody in a white coat kind of standing around saying, please do this. It's totally possible to do. I don't know about you, but I've done a lot of these experiments in EEG labs and fMRI labs in my life and career, and I have to admit that usually by the end of them, I'm kind of going, I might be drifting off, or I might be kind of going, oh, God, when is this going to be finished? Or thinking about my lunch or whatever. It's pretty dull, right? But it's also certainly not, if you can do it once, you certainly can't do it again 5 days a week and all of that. So this is what we did instead. So this is a game on a tablet. We call it AstroTap. And what happens is these spaceships move around. They stop, flash, and open. And then inside, there may be something. Now, this is where somebody has been playing. There may be an alien inside, which you're meant to respond to by pressing a button here. And like shoot the alien, don't shoot the astronauts. That's the task. So the alien is the target, like I think was a red circle. The astronaut is the non-target, like the green shaped red pentagon or whatever it was. So we do that, and we spend a lot of, we've got a team of nearly 40 people. I think 10 of them are PhDs, and it's mostly in cognitive neuroscience, bit of a mix. We've also got biomedical engineers and kind of analysts, and machine learning people, and then a load of engineers of software engineers, hardware engineers. And we spend a lot of time basically turning those dull things into things like this, which is turning it into that is relatively easy. The really hard bit is not breaking the science while making that translation, right? So that's a tough bit. And for example, I don't know, those of you who know this may have copped on that the fact that the thing stops, expands, and flashes is like the fixation point, right? So if it does that, you go, okay, I'm gonna look at that, and you don't move your eyes, right? Because eye movements mess things up. And if my eyes were over here when the thing opened, then well, the timing will be off, right? Because I hadn't actually seen it when it was going to appear, and so on and so forth. So we do this behaviorally, and we've got other. This is probably one of the most gamified tasks we have, and it's not always necessary to gamify. Sometimes you just make it more kind of pretty and neater instructions, a more kind of self-guided, more passive task. But all of that comes in then. I'm trying to remember now the order of the slides. I think we've got a picture of the headset in a minute. But we have the headset tablet-based tasks, and these things all come in through some kind of machine learning AI style. To be honest with you, now when people say AI, they really mean with computers. It's kind of dumb not to do it with computers, but anyway, we use kind of the state of the art, the best available and appropriate computational methods to take in that data and tidy it up and do automatic quality control on it. Because in academic science, in clinical science, usually there's always kind of a human in the loop in taking EEG data sets or neuroimaging data sets and processing them, pre-processing them, and all that. So that all has to happen automatically and has to happen immediately. So that if somebody's at home doing a task like that, within a minute or so of them finishing and uploading the data, then you've got a dashboard that says, here's kind of an overview of the data that gives you a sense of its quality. So just to give an example, say on that alien game, it's pretty easy to get it right nearly all the time. So most people get it right like 97% of the time, or 95% of the time. If somebody gets it right, say 60% of the time or 30% of the time, something's up. Maybe they misunderstood the instructions. Maybe they thought you're meant to shoot the astronauts, not the aliens. Maybe halfway through the session, the DPT calls the door with a package. Maybe they're watching TV or who knows what. Anyway, we kind of have automatic thresholds and criteria in the system that say there's something funny about this session, and then the clinical staff or the research assistants, whoever will run the study, that could be kind of kind of flashed up to them. It'll be kind of promoted to them a list of flags, and then they can make an informed judgment what to do, maybe ring the participants up and say, are you sure you understand the thing, or were you interrupted, or whatever. So that means that you can do these long studies and not get nasty surprises at the end of a month or 3 months or 12 months that somebody totally misunderstood how to use the headset or the games. So let's see, maybe I should do it in order. This is what it looks like from the patient point of view, or participant point of view. This is a real user in Belfast. We joke that all of our users get their hair done before sessions and live in pristine Airbnbs. But it is an Airbnb in Belfast, but she is a real user. She did get her hair done. And you'll see that what we try and do here is we try and have kind of consumer quality ease of use, but then clinical quality data, which again, I'll show you some evidence for in a minute. Just you get a quick look at the headset here, but you see it's made out of soft materials. I don't know if you can see in the, I'm sorry, actually I should have brought one with me. Okay, so it comes in a little box this size, right? And you can send people home with it. They've got little plastic pin sensors, which you only half see here, kind of in there. You can just about see it. Little pin sensors, kind of like a comb, right? So they're soft plastic, and they've got silver chloride, which is the same conductive material that like conventional EEG sensors are made out of. They have that chemically bonded into the plastic. And that means it can be conductive and soft. And softness means that it'll, let's say, firm enough to get through your hair, soft enough to conform to the shape of your scalp, and to kind of get as many touch points as possible. And also because it's chemically bonded in, that means that a lot of other sensors, which are kind of similar design, have a coating which after a while will just start falling off, start flaking off, right? And then it won't last very long. Whereas these things are rated for thousands of uses. I'll be clear, the sensors we get from a company called Neuro, they're a research EEG company out of Germany, out of Berlin and like the Netherlands, which are great, fabulous partners of ours. And so you pop the headset on, the tablet says, put it on this way, it reminds you of the instructions. It says, make sure all the sensors are connected properly. And that setup takes a few minutes, maybe 3 minutes or 5 minutes. And then after that, it would say on the tablet, and today, these are the 2 or 3 tasks you want to do. You want to do a memory task, a resting task, an executive function task, or something. So that's the platform. The question is, how well does it work? Now, there are different parts of that question. Will ordinary people actually use it repeatedly and use it reliably? Will people who are impaired, will patients use it? Will all the data get uploaded successfully? What will the data quality be like? So we sat down, as I said, with the 10 pharma companies, and they said, okay, well, if you want to test it, here are the kinds of studies you should run, the kind of scale, the type of design of studies. And we've got great partners. So we've got in the UK, we've got Oxford, Cambridge, Bath, Bristol, Stirling, and another group called Recognition Health. So a group, I think 6. I think we've got 6 sites in the UK on an Alzheimer's disease study. And then here in Ireland, involving the NHS, obviously, here in Ireland, we've got with TCD, with Orla Hardeman, TCD in Beaumont, we've got an ALS FTD study. FTD, sorry, is frontotemporal dementia. ALS is what was actually previously known as motor neuron disease. And these are the 2 studies. The one on the left is the AD one. We're about maybe 2/3 of the way in the recruitment. It's a 12-month study. We've got 2/3 of the people on board, and they have a certain selection of tasks. They have sleep, whereas these guys don't actually. For some reason, I listen there, but we're doing sleep tracking with them. And then here in Ireland, we've got 10 frontotemporal dementia, 10 ALS motor neuron, and 10 healthy. And they have another selection here, but we had kind of 1 or 2 extra tasks. In particular, we've got a flanker task, it's an executive function task, but kind of a similar mix of tasks. And I think here we should have memory match. We should have the mismatch negativity, which is a passive auditory oddball task for those of you obviously know ERP research. And so what I'll do is I'll show you some kind of high-level results from this, which is just hopefully just kind of communicates that the whole approach is feasible, because when we did this, we're breaking a lot of rules. So, and on purpose, that we kind of, so first of all, EEG is usually uses wet sensors. We get a better connection. Absolutely. Usually it's wireless. It's usually played with these very kind of carefully controlled and carefully engineered tasks, which are very pared down for a good reason, because it means there's not other stuff going on the screen, which could unintentionally elicit other processes in psychological neural processes. And you've got in a lab control over temperature and lighting and sound and all those things. And we're just saying kind of, and of course there's also somebody there to make sure that the person's actually doing it, right? As opposed to going off to make a cup of tea or something. So there's a lot of risks there. There's also, we also don't have humans checking every data set, right? So with all of these different, deviations from standard procedures result in rubbish or something useful, right? So here is from that study. I'm not sure if this is from which of the 2 studies it is, but this is an older participant, so they'd be aged of a similar age to the patients who are all over the age of 55, but slightly older average age on the ADs and slightly younger. I mean, still old, but not quite as old as the average on the AD ones in the FTD ALS one. And you probably can't read all of these things around here, but these are just some of the blue is the cognitive ones, the orange are the EEG ones, the green ones are sleep, the red one is mood, and the purple ones are language. So these are some of the endpoints, as they call them, the pharma company, or just kind of measures, which according, that we in advance in the statistical analysis plan we wrote with the pharma folks predicted based on literature should be discriminative of these conditions, right? And this is a healthy older person. That grey line there is kind of normal for this group of healthy older people. You'd expect healthy older people to all be fairly close to that. And this is based on, I think, these are based on 10 sessions. So you could say, 5 days a week for 2 weeks, for example. Now, I think there's a lot of work for us to go into whether we can pare that down to 2 or 3, but we'll see anyway. For the moment, that's it. That's what we have there. And this here is an Alzheimer's patient. So this is one of, we've got like 35 or something so far in the Alzheimer's study, but it's kind of representative of the kind of thing you see. So you'll see that the response speed, if you probably can't read this, but anyway, this big blue thing here is showing the response speed is much longer, so they're slower. Their executive processing is impaired, their memory is impaired, their theta power is higher, which is unusual, their alpha reactivity is unusually low, their P300 is usually slow, they wake up more often at night than you would expect. They take sleep efficiency, means it takes them longer to go to sleep than you would expect. But their language is more or less normal. Like this is one individual, this is not, right? But they're mostly things you would have expected based on, the literature. This here is, the last one was from the AD study. This is from the ALS FTD study, so this is recorded in Dublin. And here is a normal from that, a neurotypical of control. And then here is an ALS patient. Again, response speed, actually quite a similar pattern to the AD patient in the cognition, except that the memory isn't impaired very much. The EEG is not dramatically different, but the language is very different, and the executive processing is pretty impaired. And here's the FTD patient again, memory fairly intact, executive processing very impaired, language very impaired. So there are kind of the point-wise differences to what you see in the AD patients. And kind of if you put those things together, the idea, so this is the big idea is kind of a print like that can immediately visually kind of tell you what kind of patient you're looking at. So it's that collection of symptoms or measures that collectively tell you somebody's one disease or another. So they could be used for differential diagnosis. Is this an older person who is just, is this an older person who's presenting, but it's actually depression and say associated with sleep disturbances that's causing their cognitive impairment, or is it Alzheimer's disease? Or if it does appear to be dementia, is it Alzheimer's dementia, which is the most obvious one, and people are very often diagnosed with, or is it vascular or frontotemporal dementia or Lewy bodies dementia? That this should tell you that, and that's kind of the dream, is to be able to do this at large scale, and we're already doing it at large scale. We don't have thousands and thousands and thousands of devices. We only have hundreds of devices, but this is the sort of technology which can be used at low cost all around the world sooner or later, if you have, if you got the critical mass. So then I'll just go back then to why this would be useful in drug development. So people who are developing new therapies usually want to understand kind of this 360-degree view, this broad spectrum view of all the different ways that a therapy could affect somebody. So they want to have all those domains. And they also want to tell that as quickly as possible. So typically in a drug trial or any therapy, a medical device or some other therapy, you might have a group. Say the greens are people who are neurotypical, who are just aging naturally. The red stroke blue is your patient population being recruited into a trial. So at this point in time, they start taking the new therapy, it's administered, and say the red people are on placebo. So unbeknownst to them, they're taking just a sugar pill or something, or some sham medical device, and that's the term, is sham. That I don't mean that in a derogatory way, that's the technical term. And then the people on a working drug are declining more slowly. It's the blue. And usually you would measure something like, say, the ADAS-Cog. It's a paper and pen clinical assessment, say at month 0, and assess it again at month 24, and then measure the difference, right? Now, the thing is, all of those instruments are individually, somewhat noisy. There's always a little bit of uncontrolled variation, random variation. And then there's the fact, which isn't illustrated directly here, but our cognition changes systematically from day to day. So like if you test me today or tomorrow, the day after, I got off a plane from Florida 2 days ago. So if you tested me yesterday afternoon, I would have been a bit of a shambles, right? Whereas if you test me today, I might not be so bad, right? Or I might be in a good mood, or I might have drunk too much coffee or not enough coffee or whatever. So there's always a risk of taking a single snapshot that you'll just be wrong, right? The day is an unusual one, unusually good or unusually bad, right? So if you're able to either in a short period of time record a load of time, say 5 days in a row here and 5 days in a row here, you can aggregate over those and get a better read for that point in time here, because in the world of Alzheimer's disease, your disease doesn't progress very much in 5 days. So testing Monday and Friday, it's okay. Or you kind of go periodically along it, and then you hit kind of trend lines, and those two trend lines will be easier to differentiate. So that would mean that, I suppose one thing it could mean is you could detect a really, really subtle effect in a drug and convince the FDA or the EMA that you've got a useful drug, even though it's got tiny clinical benefit. One thing you could do with it. But I think what therapy developers really want to do with it is they want to be able to do the trial with less people over a shorter period of time. And that's what we should kind of, those studies I showed you earlier, they're designed to measure that, to measure what is kind of the data power advantage, statistical advantage of multi-domain repeated objective measurement over time to see how much better that works. So yeah, that's just an illustration of that. And so that's the end of the sort of the big vision bit, if you know what I mean, and then I'm about to go into the more data bit. Just check how am I doing for time.
It is 6:12.
Okay. So any questions there, or will I just go straight on to data? I'm really lucky to do all questions until past, and then I won't have to show you data. I'm joking. Data. Okay, data. Okay, data. Okay, so fair enough. So first one, do people use the bloody thing? This is the first study that we ran. This was back in 2018, I think. And this was done. I was a faculty member at Queen's at the time, and I hired my postdoc, Alison Buick, who's now our director of clinical programs. And we asked 90 healthy older adults. I would say 90, and this is Ali's slide. That's what she always says. It's not 90, it's 89, Brian. We were trying to get 90, and we got anyway. So it's 89 healthy adults, aged 40 to 80. These are all neurotypical, and we asked them to do 30 minutes per day, 5 days a week for 3 months. And we didn't pay them anything, which, especially when you say it's America, people are surprised. But it's normal here. It's not pay people to do these things. And also, I'd say for kind of no good reason, right? Because they weren't getting anything back. You know, it's not fair, right? I mean, they weren't getting any clear return. So we weren't, for example, giving them a dashboard that says, oh, here's your memory, and this is how you compare to other people of your age and stuff, because that would obviously be, well, unethical, because we'd be afraid they might look at it and say, oh, God, there's something wrong with me, or no, I'm fine, I'm a super performer, I'll go out and drink loads or something, I don't know. So we didn't give any feedback, so people weren't getting any kind of, there was nothing really to motivate them to do it. But despite that, we got, for those aged kind of 40 to 55, we got about 70% compliance, 55 to 65, about 80% compliance, 67 and over, we got 90% compliance. So over 12 weeks, that's the purple lines, we wanted them to do them 5 days a week. Sorry, and they did on average 4.5 times a week over those 12 weeks, and pretty consistently. And this went over Christmas. We had people doing this in Australia on their Christmas holidays. I was flabbergasted. I was really surprised that people did it so often. And one thing I often say is this is done in Belfast. This isn't like Santa Barbara, where everyone's like super healthy and like, you know, super tech thing, or it's not like Ikaria or something where everyone lives, you know, these islands in the Mediterranean or Japan where people are unusually healthy. This is like a really, you might say an ordinary Western city, or maybe even a Western city with maybe worse mental health and kind of cardiovascular health statistics than many other, you know, it's a post-conflict society. So we were really pleased with this. This is a publication, there's a Frontiers paper on all this. Most of this stuff I'm going to show you is in papers or posters. Then another question is then kind of construct validity. So if you measure things in this unusual way, do you still see patterns that look like the patterns you'd see from a similar group of people in the lab, right? So this is a resting state EEG. People watch a restful video for an hour with their eyes, a minute with their eyes open, a minute with their eyes closed. So it's super short compared to what you do in the lab. And this is the frequency breakdown of that frequency spectrum. I don't know how many of you are familiar with that, but it turns out that your brain has kind of a fundamental frequency. Your brain kind of kicks over, as it were, at about 10 hertz. You know, 10 repeats, 10 waves a second. And you expect to see that big bump there, which you see. And we see that as people get older, it's called the alpha frequency. The alpha frequency power goes down with age, which again is expected. And also, it's a very slight pattern, but it also gets lower. So it might start off, the 40-year-olds might be more like 11 hertz on average, and the people in their 80s may be more like 9 hertz, or the 70s, 9 hertz on average. This is that P300 game, where we see kind of the first couple of tenths of a second after the stimulus appears, the image appears, or the spaceship opens up in this case. You've got visual processing, and then the P300 itself, which is a metric of, my favorite account of what it means is from Redmond O'Connell, which I'm sure you're all familiar with, which is that this is your neural system accumulating evidence to decide whether I'm going to respond, whether it is the thing I'm looking for or not, whether I should respond. And the size of this, kind of I suppose that the area under the curve of that component there is indicative of your, I suppose, decision-making efficiency, for want of a better. Again, always with these things, trying to interpret neuroimaging data or neurophysiological data and imposing a psychological construct on it is always fraught with risks. But anyway, there's good reasons to think that's a fairly likely explanation. It's the one that I prefer. In any case, you expect, according to the literature, that gets kind of weaker, as it were, with age and later, and we see all of those patterns. And we have other data which we can show. We've also done, we don't show it here, we've done things where we've given people, worked with a German university, a guy called Martin Walter. He's an academic psychiatrist who does a lot of work with ketamine, with fMRI, and with EEG, where we give people a dose of ketamine, and we see does our unusual way of recording things show the same patterns you would expect to see in a more conventional setting. So that was healthy older adults. These are then the studies, the AD and the ALS, frontotemporal dementia. So Alzheimer's disease, frontotemporal dementia, and ALS studies. This is kind of a view from that dashboard system we have that shows this person here who over that many sessions has done every single one, complied, adhered to every single one. This person dropped out early. I can't remember. It may be, maybe they had an illness or something, I'm not sure. And then the ones which are, let's see, the ones which are yellow are ones which are complete, but there's something about it might look a bit funny. You should go in and check if it's all right or not. And then the orange ones are ones that are not complete for some reason. So that may be that either it could be the person gave up halfway through. It could be that the battery ran out on the device, they forgot to charge it. It could be that there was some difficulty uploading data to their Wi-Fi, things like that. But anyway, we got pretty good adherence. And here, actually on that ketamine study, we got 99% compliance. But even so, with healthy older adults, that was across all of those ones I talked about, it was about 80. Actually, no, this was another study. This is one we did with Francesca here in Rob's lab. We did a study that we got 80% compliance on them. They were 55 to 80. AD patients right now, early days of these two studies, were getting around 70% on the FTD ALS and around 80% on the AD patients. Now, that's at the start of the year. I would not be surprised if over the year that goes down. But anyway, so far it's going pretty well. And here's just an example of some data. So we were kind of proud of this one. So this was, from a technical point of view, this is where we worked with Pivotal. They're that Oxford-based company to measure mood. They objectively measure mood. I didn't mention them before, right? Okay, so I don't think, yeah, okay. So the pharma companies, when they said, okay, these are all the different assessments we want, they said, okay, you've got some assessments which are great, or maybe you can develop something or copy something from literature. But here are companies that have already developed something and they're great, and we know they work already. So work with them instead and find a way to integrate their technology into your platform, into your system. Yeah. And one of them is Winterlight Labs. They're a great company out of Toronto. They're really good language scientists, really good computational linguists, and they take recordings of natural speech, like, I'm describing a picture, or tell me about your day, or repeat this list of words, or read this paragraph or something. And they pull out metrics of things like how rich your vocabulary is, how kind of intricate your sentence structures are. We sometimes joke, do you speak like Donald Trump or not? If you speak like Donald Trump, kind of simple words, short sentences, or kind of more articulate. And I'm not sure. I mean, Donald Trump used to speak more articulately, so I'm not sure whether he's doing it on purpose, or whether, who knows? It's an ongoing debate. In any case, so we work with them for language, and then we work with a company called Pivotal out of Oxford. They were Oxford spin out like 20 years ago or something, for mood, and they have a task where you've got faces, a series of different emotional faces, and you just have to press a button. Is it happy, sad, disgust, angry, or whatever? But they've got these very fine gradations. You can have like 100% happy, 50% happy, 10% happy, and then you can see these very fine biases that if you present ambiguous faces, equivocal faces to people who have a mood disorder. They may have an inappropriate bias that they see negative emotions where they're not actually there, right? And so we got that in there working, doing that behaviorally, and we're recording EEG at a really fine temporal resolution over it, and then we get these space ERPs. I don't know if you know the M170 is what you see when you present. That we've got loads of neural architecture here for processing faces. So I show you a face, you get M170 whether you like it or not. And this is just examples of us having M170s from a single session from an AD patient in England on the system in a session where they're doing all these tasks over half an hour. So just pleased to see that happening. Okay, more. I just speed along. Oh yeah, okay. So here's the harder. So that was more kind of usability style stuff. Yeah. By the way, people say they like using it, but the more important thing is, do they consistently use it? They do. Here we're looking at reliability, and this is work, partly work of Florentine Barbet, who's studying her PhD with Rob actually this month. Our wishes are with her, so she could has a happy write-up. And we're also looking then at test-retest reliability. That was Raju, who's also a Trinity graduate, who was in Luke O'Neill's lab. He works with us. So I'll show you this. So here we're talking about quality. So a really common question you say, well, is your data as good as in the lab? And you say, well, it's a complicated question, but or the different ways you can answer it. It's not a complicated question. Different ways you can answer it. And here are a couple of different ways of answering. So one thing is people say, what's your signal to noise ratio? Nobody actually knows what that means in ERP land or in brain imaging, because you don't actually know what signals or noise without sticking loads of let's see, not only an unethical but a technically unfeasible number of wires into somebody's head. Do you know what the actual signal is to be able to distinguish it from noise? Right? So you don't know. So signal to noise is kind of it's just, you can't do it. So two things we looked at. One is Stephen Luck. So Stephen Luck is kind of like what do you call? He's kind of like the godfather of ERP research, of kind of task-driven EEG research. He's out of UC Davis, and he has come up with a new measure because the whole world of EEG and ERP research couldn't agree on a measure of noise. He came up with a new one and published about a year ago. It's very nice of him, and it's a good measure. It's very simple. It's just standard deviation divided by the root of the number of things you're sampling. So you'll see if anyone's ever seen like a t-test, or they've all got kind of the elements of that in them. It's kind of like a core part of a lot of statistical inference tests, or statistical confidence intervals as well. And you can apply that to frequency decompositions or ERPs. The other one is test-retest reliability or intra-class correlation. The question here is, if I try and look at the same frame pattern again and again and again and again, how kind of tight a window will I have of confidence about where exactly it is? What's the value? Like, how big is my peak? How big is the top of that P3? The peak of that bump? How high is it? How small a confidence interval is basically the question being asked here. This one here is, if I measure that on different days, does it give me the same answer? Right? Now, I'll just say about ICCs, and let's just how much time do I have left? Okay. Okay, in questions we can talk about why ICCs may or may not be a good idea. Standardized measurement error, this is the gold standard. So this is data. You remember Stephen Luck, who had that new measure. He also brought out a data set and said, here's kind of the way EEG should be recorded in a lab properly by somebody who really knows what they're doing. I mean, he didn't say that, but he is kind of really good. So it is kind of like a gold standard. And he had a particular measure of this noise for his oddball chart P300 and for his relation negativity. If you look at one of our sessions with similarly young and comparable participants, it's a bit higher in clinic. If you go home, it's worse again. But if we aggregate the data from two sessions, we're as good as our in-clinic session, still not quite as good as the gold standard. But if we aggregate 3 or 4 of our sessions, then we're actually better. Well, with 4 of our sessions, we're better than an in-clinic session, right? Now, see, that's more participant time. But the main bottleneck for research typically is research time, right? I mean, that's and lab time and what's called booth time and all that. So if you give somebody the headset, give them the tasks, you send them home, say do it a few days in a row, you get data which is as good or better than you would have got in the lab. Or as reliable. As is less noisy than what you would have got in the lab. Okay, that doesn't mean better. It's a different question. That's one. And then error rate relation negativity is harder to get. Again, we can discuss why it's harder to get as good ones on that. And then last thing is if you did the resting state, so remember I said if you do a resting state, you've got this alpha peak, this fundamental frequency of the brain. In a lot of studies, they've found that the size and the frequency of this not only goes with age, but also goes with disease. So this is like a marker for disease. We take the data in, we process it automatically. Our algorithms go in and pick out these peaks and then say, okay, on PZ, that's a location here from this person on this day. It was 19 decibels or something, right? So that's the marker that you could use, for example, as part of a diagnostic algorithm. Question is, if I tested that same person 3 days in a row, how similar an answer would it give me, right? And ICC measures that, so this is the peak power. And we found that if we did multiple in-clinic sessions, agreement between 2 sessions was between 0.8 and 0.9, which is high for ICCs, if you have to be familiar with ICCs. If we go at home, goes down below between 0.7 and 0.8. But if we aggregate over 2 sessions, we're back up at 2 at-home sessions, back up at 0.9 again, or 0.8, 0.9-ish. And peak frequency is a little bit harder to get, but again, we actually did really well after aggregating over a couple of sessions. Again, these are 3 different locations at the back of the head, O1, O2, and PZ, and which is where you measure this most effectively. And then this is an ERP, so this is from this flanker task, which again, we can go into details if we want. This is the visual processing component, and called the N1. And we started off getting it around 0.6 from a single in clinic, 0.6, just under 0.6 for just at home, but then getting up to 0.8 from 3 at-home sessions. And here actually we compared to, for this analysis, which we haven't published yet, well, there's a poster on it, sorry. We compared to work that Ian Robertson did with Redmond and I know somebody, Cassidy, I haven't met that person, I think it was back in 2012 or something. And we basically do as well as they did in the lab. Because not many people, it's actually hard to get data on this because not many people go to the bother of doing an EEG session more than once in the same person because it's just too much bloody hassle. There are very few studies that tell you how repeatable they are, but Ian and Redmond did one of them. They did a good quality one. I think it's the best one I know. It's not just because I happen to be in Dublin and happen to be standing in Trinity. I think it's the best study we know of. And that's it. That's why we think the system works, and that's why we want to work towards, first of all, helping therapy developers to find the right patients, get them into the studies, and get an answer to whether a drug works or not as quickly as possible. And by the way, you may be surprised, drug companies are also often quite happy if early on you can tell them the drug's not going to work. Because when they say, okay, they've usually got this big, long queue of drugs they want to test, but only the resources to test a small number of them. And then from there to be able to get it into doctor's surgeries. So we can help individual patients maybe get more understanding of their condition, and we can then precision target existing drugs and the future drugs. The right people get the right drugs at the right time. And that's me done.
It was really an interesting talk. So, anyone questions?
Yeah, I don't mind saying. I'm sorry I ran right up to the hour on my talk, but I'm very, very happy to stay for questions. Yeah.
Mine's kind of, I won't say technical, because I don't really understand computers. So one of the things that struck me there, that's never really struck me before, you're doing the headset, you're doing the tablet, they're not connected physically. How do you make sure that that's time locked properly? Because so I work in rodent EEG, as you know, and that time locking is an issue with behavior. And so I was just wondering, how do you make sure how does that work basically?
I didn't mention it, it's a really important point. It's also something that I can't talk about because we've filed a patent on. Okay. But, good answer. But we do manage, despite the fact, so you've got, it's important point. So you've got a headset, it's transmitting over Bluetooth to your tablet, that's streaming. Any networking protocol at all, especially wireless ones, are not especially reliable. So, something can get sent and not arrive and then has to resend it and things like that, or maybe delay it. Things might arrive out.
I play video games online, so yeah.
Right, exactly, there you go. Yeah, exactly. You said you didn't understand but we do manage to get synchronization plus minus 2 milliseconds between the headset and the tablet. So it's possible to do.
Yeah, I figured they were a second, but it's just, I was curious as to how.
Yeah, and if we hadn't, then you would see, the reason you would know that is because something like this would not look like something like that. So maybe something that is not obvious to everyone, but the way you do ERP research, so what's happening when your brain is working right now is, say I show something to somebody their visual cortex respond to that, say, fish popping up, which is what happens in this game. But your brain's doing loads of other stuff at the same time. And I'm recording here, and I'm successfully recording the effect of that fish plus everything else that's going on in your brain, like the fact that I'm not falling over and I'm breathing and I'm thinking about when I'm going to get out of this bloody experiment on my lunch. And all those things are overlaid, right? So if you want to pick out this pattern, you don't show them one fish, you show them 50 fish in a row, right? And then you take, each time the fish appears, you've got really fine time lock between like a continuous EEG signal and all these, you've got these little bits like here, these little lines that say, okay, here's when the fish appeared, another fish appeared, another fish appeared. And you take out all those little slices and line them up and average them. And by averaging them, all that background variation gets more or less washed out, turns into more or less a flat line, and then you see the actual stuff, right? So if we didn't have good timing synchronization, all those different fish effects, this is, let's see, this is 0, that's a 1, so that's like half a second. This is about 200 milliseconds here. So 1/10, 2/10 of a second from 0. Each of those would have happened at slightly different times, right? If the time wasn't good, and this would all be kind of smudgy. Do you know what I mean? Mm-hmm. So the fact that this has got like a nice sharp point demonstrates that we've got good timing synchronization between each of the different trials, each of the different instances of when it's presented. Yeah.
Anyone else?
I'm just gonna get some water over here.
Yeah, sure.
I was gonna ask benefit text for you, but I do have a question. You mentioned that this could be used to distinguish between Alzheimer's and depression, and I was wondering, like, can the symptoms of depression could be measured like this, and then maybe you could get a grip on whether or not someone was responding to depression medication based on this? Would this be another application?
That's exactly what we want to do. Yeah. Now, I have to say, depression is one of the harder ones. In depression, with some of the EEG, you may be able to measure. Measuring with EEG whether somebody feels depressed doesn't work very well. Mm-hmm. What may work well is that thing of presenting those faces. Mm-hmm. So if somebody is seen, if you show somebody a load of faces and say, half of them are really easy to tell, happy, sad, blah, 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 half of them are really hard, the person who's depressed, when they're unsure, might tend to see anger or fear or sadness when it's not there. If you improve the disease, then that bias may disappear, and they may just have like a 50-50 happy, sad split, or a split which is a bit better than what they had before you gave them the drug. Mm-hmm. Another way it can be used for depression is that a lot of the drugs that people use in depression, for them to work, for you to feel less depressed 3 weeks later, or 1 week later, or 2 weeks later, have to first start changing the biology or the mechanisms of the brain. And some people may just, for whatever reason, the drug may not engage successfully. Mm-hmm. So you might be able to detect on day 1 or day 2 or day 3 that this drug didn't even start changing your brain activity, therefore there's no hope that there's any change 3 weeks later. Exactly.
So you could change to a different drug earlier and maybe save time and...
Exactly, so you can iterate through, well, I suppose the first thing we hope to be able to do is be able to iterate through the drugs more quickly. Mm. With enough data, hopefully we can learn to better predict before you give a drug to somebody whether it's a good fit for them, right? Yeah. It would be great if we could do it. And we're not the only people trying to do it. I mean, that's what the whole effort of, of precision psychiatry is hoping to do. Yeah, we're not alone at all. Yeah. Sure.
The presentation, my question is, do you have data that talks about preclinical prediction of dementia? Because what you've been showing us appears to be a consensus diagnosis between MCI and AD. But do you have data that shows the preclinical prediction? Because I think at this level, people are beginning to understand midlife prediction of dementia. So, do you have such data?
We don't have that data. We certainly like to do it. So, I mean, obviously, the more subtle the kind of effect you're looking for, and the less well characterized it is. So even MCI is still an uncertain. You can have the best clinical academic in the world can say somebody has MCI according to the best tools we have, and still have a lot of uncertainty about whether that person is going to develop dementia and which variety it's going to be, right? And if you go earlier than that, the uncertainty goes up, right? And the subtlety of the difference goes up as well. And to detect those changes, you need larger groups of people over longer periods of time. So it is absolutely our ambition to do that, but we don't have that. Now, the reason I'm ambitious about it, I'm kind of optimistic about it, is the fact that we're even seeing quite big differences just in natural aging. People who are perfectly healthy, have been kind of well characterized. All those people on those studies came into a really, really involved neuropsych battery. different times here in Trinity with Francesca and up in Belfast with Alison. And they appear to be, according to all the tests, appear to be perfectly neurotypical. And even among those, we're seeing the differences just being like 40, 50, 60, 70. So if we can see that, I'm hopeful that we can detect early disease too.
Quick question.
Yeah.
I might have misunderstood, but I think you mentioned that this would be useful for screening participants for clinical trials as well.
Yes. So in clinical trials are weird because usually they want kind of somehow kind of a rarefied variety of patient, right? They want the patient to keep, you don't want to have any more variation. You're trying to have a shorter trial with a small number of people as possible. You like to have as little other variation in the group as possible, right? So they tend to want to have people of a very particular phenotype. And the pharma companies tell us that it is, I suppose, uneconomic or impractical or kind of infeasible or kind of logistically too burdensome to test people as much as they'd like to test them, right? So they'll either take in a group of people who are more varied than they would have liked, or they bring people in and they have to put everyone through a PET scan, for example, which costs, in the US, costs like $10,000 per person, right? So say, for example, like I know people like, what are companies like Biogen, Lilly, who's the other one again, Eisai, who are doing these really big, Roche, doing these really big Alzheimer's trials with earlier people, are doing things like bringing in people and they need to, say, test 5 or 10 or 20 people and put all of them through PET scans to work out to find one appropriate participant. So it's costing them at least kind of $50, $100, $200,000 to find one person. Or that's that one part of the test, the most expensive part of the test. So anything that can, and again, that's time and money. Time and money means they get to test fewer drugs. So any way we can streamline that procedure would be very welcome.
I mean, I guess it's related to the previous question on preclinical science as well. I suppose you want to screen people that you have some reasons to suspect it.
Yeah, exactly. Well, yeah. So screening, I suppose, there are 3 different meanings of screening. One is some sort of in pharma trials, what they're usually trying to do is to have a cheaper and easier and quicker, a more scalable way to take a large number of people and filter them down to a smaller number of candidates who will then go into some more involved testing. It's usually that, right? And which may be early stage or may not. It may or may not be, depending. I think the whole thing about early Alzheimer's and drugs, I'm not 100% convinced. Obviously, you don't want to start treating people with very severe AD, right? You should start with, but this whole thing about going earlier than mild dementia, I sometimes feel like the reason that's happened is because people have taken a certain class of drugs that have a particular hypothesis about the mechanisms of Alzheimer's. They haven't worked with mild, they haven't worked with severe, they haven't worked with moderate, they haven't worked with mild. So they say, well then, okay, it must be because we're too late, so we're going earlier and earlier and earlier, right? And then if you do that, the risk is that you're including a load of people in your trial who don't actually have that disease, or are so kind of early that there isn't that much to fix, if you know what I mean, to rescue in the terminology. But yeah, I mean, there are a load of different ways you could use the extra statistical power, and that's one of them. Yeah.
Are these technologies being used for treatment, like non-drug treatment at the moment, or do you have any intentions with it, or is it just for pharma trials?
We could use it for anything. I mean, like we certainly have the most obvious. There are quite a lot of interesting medical device things like the light-based therapies, like Cognito. You might have heard like Cognito or other companies, light-based therapies or other simulation-based therapies. And whether it would work for, say, talk therapy, I don't know. I have no idea. I mean, I would say that kind of what the technologies we have, the measures we have, may be better suited. Well, if you're talking about psychiatry, maybe better suited to looking at mechanisms, and it's less obvious to me that talk therapies directly tap mechanisms, like a deep neural mechanism. They tap in a different way, which is not to kind of rubbish them or trivialize them in any way, but it's just kind of a different mechanism of action. If you're talking about neurodegeneration, improving memory, of course, yeah, no matter how you improve memory, through what mechanism, you should be able to detect with this. I mean, did you have something in particular in mind? Or?
Stimulation?
Right. Yeah, I think stimulation is a great one. Well, also because often, say if you're talk about something like TMS, you know, give somebody a blast of TMS, there are characteristic changes in electrophysiology that happen, you know, some milliseconds or tenths of seconds or tens or hundreds of milliseconds. I'm not sure, I don't know TMS very well, but within a short window, you see immediate kind of mechanistic markers of how well they're engaging. So absolutely, other people do use methods like ours with TMS, for example. We haven't done it yet, but you totally do it, yeah.
So can I ask you a question? Do the patients need assistance to complete the task?
Surprisingly little. So we had, but it depends. So that's a clinical judgment for the clinical trial teams at each site. So it's their job to say, is this somebody who can use it as is, or whether they should have a care partner or a study partner? And then the amount of involvement. So say somebody's with ALS, they may have difficulty just getting the headset on, right? So they need a care partner for that. And other people may need to be basically reminded that you should sit down and do this simple task, and that they're kind of kept on task, if you know what I mean, by somebody. And that depends. And we would, you know, we did the first actual clinical trial we did this with was actually Florentine went and did, Florentine, our PhD student who's also at Trinity, she went, we were asked in the middle of COVID to jump into the middle of a phase 1 trial in Australia, because they had a load of imaging markers and people didn't want to travel to the imaging centers anymore. So they said, okay, we need something instead. So we jumped in the middle. Florentine had to like fly over, stay in quarantine for 2 weeks and all that. So we felt really sorry for her until she started sending pictures of her swanning, or like surfing in Perth and things like that. And we were kind of like, okay, we don't feel sorry for you anymore. We were all sitting here in our rooms, like in Ireland. She was not able to leave our houses. But there we had, just to give you an example, we had participants in, say, the 20s, MACA of kind of low 20s, who were doing all of these tasks. We had other people, say, 13, 15, and for those people more impaired, we said, we want you to do more passive tasks, like the passive auditory audible for the mismatch negativity. You just kind of watch a silent movie and there are beeps going on, or you do the resting stage. And they were able to do that, and we had recognizable EEG from them in the home. They obviously had a study partner, but you're right. I mean, it does have to be appropriate, and you do have to have, you know, adequate support in place to make sure it works. But,
Yeah, because also the familiarity with technology can have an effect, and maybe if the goal is to help improve the identification of patients for clinical trials, maybe in the end you will only be able to assess patients that are familiar with technology and can do this.
I disagree in the sense that it's, if that's the case, I haven't done my job properly, right? So it's my job to make sure that these technologies are easy to use and can be introduced to anyone in 20 minutes. You know, if that's not possible, I failed. You know, we failed, and I think we've got a lot of evidence that we've done it. We're doing actually a pretty good job at that. And again, as I say, like, you know, Belfast is not Santa Barbara. You know, you have all these people in their 80s just using it again, or 70s, using it again and again and again, and not actually finding it difficult. You have to do simple things like, you know, make sure that often the things are like, I can't connect it to my Wi-Fi. You know, things like that. So you know, put a SIM card in the tablet. You don't need to do it anymore. You know, there are a lot of kind of practical ways to deal with this, and people are often much better at using these technologies than a lot of these to do with perceived difficulties. Say, oh, they're nervous about it. They're not sure they can use it. But if you design the interfaces properly, it should be possible, and it is possible if you do it properly. Yeah.
Actually, that's a really good point that Saul is making in terms of selection bias, and I'm just curious. I'm just curious in terms of your projects, if you are looking to work with other countries, which are, let's say, countries like India, where you go into the middle of a village, they have they can't even hold paper and pencil.
Mm.
So we can't expect them to use this on their own. So.
Well, so I have no knowledge.
I'm just wondering if part of your vision is also to test in, even here, even within Ireland, more indigenous native populations.
I would love to do it. So I wrote, I mean, Agustin isn't here tonight, but I wrote a grant together with Agustin to try and do it in Chile, right? Mm-hmm. And to find different parts of, and try and find parts of the country or parts of Santiago where there are different levels of socioeconomic opportunity, let's put it that way. I think that'll be interesting. I'm not familiar, like I've been to India for 8 hours I've changed
I mean, most
planes,
people
but
use a smartphone, so but
exactly, yeah, yeah, yeah.
for sure,
Exactly.
yeah.
I think it is doable. I would expect it to do. If that has to
Yeah.
be tested, I would expect it to do. I know rural China very well, or different parts of China, and kind of back beyond parts of China. And I think we can, if we do our jobs properly, I think it should be absolutely achievable. And whether it's exactly the same, no, and it would never. But again, that's exactly why. I mean, when I say if you do your job properly, doing my job properly means testing those things.
Yeah.
I would say not testing those things. First, asking people before you test them, right? Going to talk to people and say, you know, is this a good idea or is that just a really stupid idea? And how should I do things right? And then testing it, and then if things are found out, then fixing it. You know what I mean? So that needs to be done, and I would love to do more work like that. Yeah. I mean, I spent all my time, going to conferences like, you know, like I mean, Boston, Florida, Boston. Like, if somebody says, here's an opportunity to do something in India, I would be there like tomorrow. I would love to do that. Yeah, yeah.
Because I think it's necessary because it's very important. Like what we are talking about, scalability, and we're talking about blood-based biomechanism as being a good predictor.
Yeah.
The question is, does it work in like African ancestry?
Yeah.
Because this has been a serious issue. Whether these things are transferable in some other ancestries.
Exactly. Yeah.
So I think
absolutely. Yeah. Well, I know, for example, sorry, we'll get to you in a second. You've been waiting a while. I know that, for example, EEG is used particularly in Cuba, right? Because they didn't have access to MRI, right? Because of sanctions. There is actually I know of some companies are developing a different headset from ours, like a more or less kind of disposable headset. Yeah. It's only a couple of sensors on the forehead, like $15, right? And I think our headset will, if we make a lot of our headset, and we will in the future have a smaller headset with a smaller sensor count, it'll be a lot cheaper. But I aspire, that's exactly what I want to do. I want to be able to just be so cheap that they can really be used anywhere in the world. Because, and as I say, the thing is, even in a country like Ireland, now our health system is far from perfect. There are loads of things wrong with it, but we are also one of the richest countries in the world. It's loads better resourced than most health systems in the world. Even here, we're not getting it right? So we can. I want to start. We're starting in places like this, but if there was any opportunity to do in other parts of the world, I would do tomorrow. Yeah. Obviously, you need to fund it. You know, you need to get a funder. But I would love to do that. Yeah, yeah. So if you've got a rich uncle or something, yeah, yeah. Sorry.
I think we can just take one last question. Sorry.
I was just wondering, like, if this, how you think or you are doing to try this in neurodiversity, for example, to be able to determine it when a kid actually, for example, ADHD or something like that. Like, you know, sometimes the diagnosis is pretty kind of random, you know, like, oh yeah, you had ADHD, you just go to this medication, but it's so tight and so different in the kids and so common right now that kids can fall in the neurodiversity range.
So we are, it's something I know very little about, but we are starting a study with Rob Whelan and Jane McGrath through Trinity in probably January, February on it. So we're going to do, I think they're hoping to do 300 kids in here in West Dublin. Well, actually a few different clinics around the world, around the country, HSE, but yes, we're just starting to look at that. Yeah, exactly. I think we need to think carefully about getting the interfaces right. Also, maybe sensory issues. Some kids have sensory issues, putting in their head, they might feel a bit uncomfortable. So I'm sure we'll learn something at the start, and hopefully.
I mean, even like, for example, I don't know, like I had anxiety, and some of my problems are really focusing. You know, like the medication is like some medication will help me to focusing more in the things, and this kind of that will help me to just means this medication is working behind of just made me feel more comfortable, but to actually improve these tasks that have been altering myself. Yeah.
Exactly. Yeah. Exactly. So it's our first step into that world will be in this study next year. Yeah.
Okay. Thank you so much for coming here.
Video offer.